Hello, and welcome to the video lecture for topic 21, Electrophilic Edition Part 3, Boron Reagents and Alkynes. Now, in an ode to my youth, I would like to inform you that today's video lecture is brought to you by the letter B and the number 5. That's right, this topic is almost entirely about the element boron and how it behaves in electrophilic addition reactions. So, first, we're going to take a look at what is the core compound that most of the reactions we're going to see today are based off of. And it's based off of this reagent called, or this compound called borane, BH3. And so if we recall from our previous topics that talked about boron, we know that boron has a formal charge of 0 when 3 atoms are bonded to it, and that it has sp2 hybridization with an empty p orbital. And so what we can infer, or what we can deduce based on this, is that 1, boron is a Lewis acid. It is an electron acceptor. What I will tell you is that it is an extraordinarily good Lewis acid. It really wants to accept electrons. But we should also keep in mind that because it is able to accept electrons, this boron atom is also an electrophile. So boron, when it's neutral, is an electrophile. It is electron deficient, and it has that empty p orbital where it is able to receive electrons. Now that we've got that out of the way, BH3 in and of itself is not a molecule that we can work with, right? It is this colorless gas. It is impossible for us to isolate it in a concentrated, pure form to be able to use it as a reagent. And even more so, if we do try to concentrate it down, it actually forms a dimer called diborane that looks like this. And diborane is a very bizarre reagent. And one of the things that should stand out to you right away is that we have this very odd situation where somehow we have made 2 bonds to hydrogen without creating a formal positive charge. And really, we know that hydrogen can't accommodate more than 2 electrons. All it has is a 1s orbital. What's going on here is that diborane is one of a set of very unique reagents that can create what we call 3-center 2 electron bonds. Right? And so we have 1, 2, 3 centers. Each atom counts as a center. And all across these 3 atoms, there are only 2 electrons being shared. So even though we have what are 2 covalent bonds here, there's not a total of 4 electrons, there's a total of 2 electrons. Again, diborane in and of itself, still a gas, difficult for us to handle, difficult for us to manage. It's actually fairly toxic. There are explosive issues with it as well, right? This is not as bad as dichlorocarbene, but it's still a nasty reagent that we're really unable to work with. Thankfully, though, we as organic chemists have developed 4 reagents that allow us to use borane, or allow us to access the reactivity of this boron-hydrogen bond that's so beneficial for us in electrophilic addition reactions. So I'm going to clear off the board, come back and show you those 4 reagents that we're actually allowed to use. So as I said, there are 4 reagents that we are able to use that give us access to this BH, this boron-hydrogen bond reactivity that's very useful for us in organic synthesis. The first 2 of those are Lewis acid-base adducts, where we have boron with its 3 hydrogens as borane. We remember that there's an empty p orbital able to accept electrons, and we can combine this borane with either THF, right, of which the oxygen is a Lewis acid. So we can take these 2 electrons from the oxygen, form a bond to boron. Boron now takes a formal negative charge, oxygen takes a positive charge, we can make this Lewis adduct between our Lewis acid borane, our Lewis base oxygen, right? And we have now BH3 dot THF is how we abbreviate the name of this reagent. It's also known as borane THF, borane tetrahydrofuran. But we can now use this to access that boron-hydrogen reactivity. The other Lewis adduct that we can make, again, we have borane, we have borane. This time, however, we're going to use a different Lewis base, dimethyl sulfide. And again, sulfur here is a Lewis base. We can use this pair of electrons to make a bond to the boron atom that puts a formal negative charge on boron, formal positive charge on the sulfur. And this reagent is abbreviated BH3SME2, dimethyl sulfide. So borane dimethyl sulfide or borane THF, right? These are two reagents we can use. The next one I'm going to show you is one that we use a little less frequently, but it's still an excellent choice for a borane reagent. And this is known as 9BBN. And what we have is a boron bridging a cyclooctane ring. Now, I know it's kind of hard to see the cyclooctane right now. You're definitely in the POGIL worksheet associated with this topic are going to be able to have the opportunity to build a model of 9BBN and see kind of how this is the lowest energy conformer for it and get to play with it in a physical sense there as well as one of the exercises in that worksheet. So as I mentioned, this is known as 9BBN. This is the abbreviation I want you to know for this reagent. But you should also know what the full IUPAC name is. This stands for 9-bora bicyclo 3,3,1 nonane. I don't need you to ever write out that full IUPAC name, but now you know it and you can use it when you feel like it. Just the name that's boxed, this abbreviation boxed here, 9BBN, indicates the structure of this reagent. Finally we have my favorite borane reagent, which is known as catechol borane. The structure of catechol borane makes it a particularly useful reagent. We have a catechol moiety bonded to this boron that has that active boron-hydrogen bond that's going to be very useful for us. So catechol borane, that's my personal favorite. You should also know that this is technically a resonance hybrid where each oxygen can at a certain point donate a lone pair to make a double bond to the boron. I'll just quickly show you here what that overall resonance hybrid looks like. So we have two partial double bonds, one from each oxygen to the boron. Gives us a delta plus, partial positives on both of our oxygens, and a partial negative on that boron atom. So here now, right, these are the four different reagents we can use. The abbreviations for them, or full names, that I'm going to expect you to know. For the rest of this video lecture, for the rest of this topic, I'm going to do all of my reactions with catechol borane. It makes the arrow pushing a lot simpler. This is one that you can always pull out when you're asked to fill in a reagent. Any of these other three are perfectly acceptable as well. This is definitely the one that I recommend you use for your arrow pushing mechanisms for this topic. All right, so now that we know what reagents we are actually able to use for as borane surrogates, right? Since we can't use BH3, we have to use one of these 4. Let's go ahead and see how they behave, right, in electrophilic addition reactions. So our electrophilic addition reactions always involve some sort of a pi bond, and I'm going to go ahead and start us off with an alkene. So here now is my alkene, and I'm going to, as is the trend with these topics, create an unsymmetric alkene so that it's easier for us to apply Markovnikov's rule. Now, recall from the beginning of this video lecture that we said that boron is going to be, that boron atom in any BH bond is going to be the electrophilic atom, right? This is for 2 reasons. One, we've mentioned it has an empty p orbital that's just ready and waiting to receive electrons into it. But something that I'd also like to point out to you is that if we think about the nature of a boron-hydrogen bond, right, and we look at the electronegativity of these 2 atoms, the electronegativity of boron is 2.0 on the Pauling scale, where the electronegativity of hydrogen is 2.1 on the Pauling scale. So hydrogen is actually more electronegative than boron. And this bond is polarized in the direction of the hydrogen atom. It's a very small difference, so that polarization is very minimal, but it is a factor that contributes to boron being the electrophile among these 2 atoms. So we'll just keep that off to the side, right? And we remember that Markovnikov's rule tells us that that the electrophile adds to the alkene such that the most stable carbocation will form. Well, when we add a borane across an alkene, we don't actually ever generate a carbocation, but that rule still applies. Our electrophile is going to add to the carbon that would end up giving us the most stable carbocation. Here if I make a carbocation at this carbon, it would be a primary. If I make a carbocation on this carbon, it would be a tertiary. So I want my positive charge to be at that tertiary carbon, which means my electrophile will bond to my less substituted carbon. The arrow pushing actually involves all 4 atoms, both alkene carbons, the hydrogen and the boron, acting in a single concerted step, where the alkene electrons go to the boron atom, and the boron hydrogen electrons, remember the hydrogen is more electronegative, so it's going to take the electrons with it when that bond breaks, goes to the other alkene carbon. This is a concerted 1-step process in this step that gives us this result. So here now, in this case, my less electronegative atom, my electron deficient atom, this is going to be the electrophile. We can think of the hydrogen, bond polarized this way, more electronegative, it's taking the electrons. We can think of this as being the nucleophile. And we see when we look at this, we see that we have obeyed Markovnikov's rule in that my electrophile bonded in such a fashion that if the nucleophile wasn't there, I would have the most stable carbocation. And this intermediate that we formed is known as an alkyl borane. So, and it does obey, as I said, Markovnikov addition. So, that's the first step in any process that involves adding a borane across a pi bond. We have this concerted process. All 4 atoms are reacting at once together. All bond making, bond breaking happens simultaneously. We form an alkyl borane where the boron atom bonds to the alkene carbon that is less substituted, or the alkene carbon that would result in the most stable carbocation. So we have followed Markovnikov's rule. Now, there are 2 different fates for this alkyl borane once we've made it. We could leave it, sorry, 3 different fates. We could leave it as is, not do anything with it, and we've made an alkyl borane. Or more useful to us is to replace this boron atom with something else. And so one of the most common things we do is called hydroboration, oxidation. So we've done our hydroboration, we've added a hydrogen and a boron across the double bond. Now let's see what it looks like when we do our oxidation. From here, to do this oxidation, we need to use two more reagents, hydrogen peroxide and sodium hydroxide. So I'm going to just clean up some space here, and let's just start off with what happens when we mix hydrogen peroxide with sodium hydroxide. So hydrogen peroxide has an acidic hydrogen, and even though its pKa isn't like super great for this acid-base reaction to happen, we will still deprotonate that hydrogen peroxide and form the peroxide anion and a molecule of water. And there's our sodium to balance out our negative charge. Now that we've been able to form this peroxide anion, it is going to act as a nucleophile. Boron is still electrophilic, and it's going to form a bond to that boron. That takes us to an intermediate that looks like this. I'm going to start abbreviating those extra hydrogens. Where the oxygen from the hydrogen peroxide bonded to the boron, and we still have that sodium cation to balance off all of our charges. Once this occurs, this CH2 group will migrate to the oxygen bonded to boron from hydrogen peroxide. When that occurs, that pushes out OH minus. And yes, I know OH minus is a bad leaving group. This is one of the rare instances where we actually do get to push it out as a leaving group to give us a new intermediate, excuse me, I'm just not happy with how that looks. Let's go ahead and clean this up. And now we've generated OH minus, and we still have our sodium anion. Okay, we're almost at the finish line here. At this stage, oxygen comes in, attacks that boron from hydroxide. The boron-oxygen bond we had before breaks, leaving electrons on oxygen. We now have our deprotonated alcohol. We now have a deprotonated alcohol. There's our sodium to balance our charge. There are the two hydrogens. There's one methyl group, two methyl group. There's the hydrogen we added at the start. And don't forget, we made water back here. Water now comes back into play. and it protonates that deprotonated alcohol. I should show you here the byproduct from our catechol borane. Just has that hydroxide group now bonded to the boron. And so in our last step, oxygen deprotonates, the alkoxide deprotonates water, and we are left with our newly formed alcohol. There's the hydrogen that we got in the very first step of our mechanism when we did our hydroboration. Here now is the OH that we added through our oxidation. And we've regenerated a molecule of sodium hydroxide, which can go on to react with more hydrogen peroxide, which can react with more alkyl borane, yada, 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 yada. And so we see that, while we need a full equivalent of hydrogen peroxide, we only need a catalytic amount of sodium hydroxide to initiate the oxidation reaction. Now, let's take a look at this product. If we recall back to when we were adding water across a double bond using sulfuric acid and H2O, we found that the OH actually added to the more substituted carbon. So by doing this process, even though our initial addition gives us Markovnikov, right? So our initial hydroboration gives us a Markovnikov addition of electrophile and nucleophile. The overall product after this oxidation process that we go through with hydrogen peroxide and sodium hydroxide gives us what appears to be opposite orientation, also known as anti-Markovnikov. But in reality, this is the initial step, the initial electrophilic addition, because this, in our entire mechanism, this is the only electrophilic addition step that we do, our hydroboration. That electrophilic addition obeys Markovnikov's rule. What we do after it doesn't count as electrophilic addition. It's just something for us to replace the boron to get an alcohol there instead. So that's one fate of what can happen when we do a hydroboration oxidation. We can replace that boron atom with an OH group, and we can make a anti-Markovnikov alcohol. So I'm going to show you the other option, which is hydroboration protonolysis, right? So I'm going to clear off anything that we don't need from the board, and I'll be right back to show you our other option for what we can do with alkyl boranes. Okay, so we saw hydroboration oxidation, where we took a borane, catechol borane in this example. We do our hydroboration that adds across the double bond with Markovnikov orientation. But this time, instead of doing an oxidation to form an alcohol where the boron is, we're going to do what's called a protonolysis, where we're going to replace that boron atom with a hydrogen or a deuterium atom. So this is hydroboration protonolysis. My spelling may be off there. I apologize if it is. So to really illustrate how this is different, or what the result of this is, I'm going to go ahead and install a deuterium in the place of that boron. However, if I use hydrogen, it'll work the same way. So this begins with an equivalent of some sort of carboxylic acid, and acetic acid is actually the most common choice for us to use in this. Here now I am using an acetic acid derivative that has deuterium in the place of the acidic hydrogen, so that we can see how this operates, and we're going to see that the deuterium actually ends up where that boron is. So in the first step, it is actually the carbonyl oxygen that comes in and adds into that boron atom to form a Lewis adduct, which was going to go ahead and look like this. So this is the hydrogen we added during hydroboration. Here now is our other alkene carbon. Here is our boron from our catechol borane. And we have now made a bond, we've now made a bond between this boron atom, the carbonyl oxygen, there's the carboxylic acid acidic oxygen, and here is the deuterium atom that I'd like to install. Here now our boron has a negative charge. That carbonyl oxygen, having 3 bonds and 1 lone pair, takes a positive charge. Okay, so this, if we notice, is a 6-membered, what we can consider a 6-member transition state. If we look at all the atoms that are going to participate in this step, we have carbon is 1, boron is 2, oxygen is 3, this carbon is 4, this oxygen is 5, and my deuterium is 6. 6-member transition states are really favorable, right? 6-membered rings have the lowest strain energy. They're our reference point when we're talking about cycloalkanes. And in 6-member transition states in a reaction are also very favorable. And so what happens, carbon, being more electronegative than boron, is going to take the electrons in this carbon-boron bond, and it's going to use them to form a bond to that deuterium atom. Oxygen, being more electronegative than deuterium, is going to take the electrons in this oxygen-deuterium bond, and it's going to come around to form a new carbon-oxygen double bond. That would leave 5 bonds onto this carbon atom, and so what happens is we break the pi bond from our old carbonyl, and we deposit those electrons directly onto the oxygen. So we've done our 3 arrows. Let's see what the end result of that is. So here now I'm just going to start with my alkene carbon there. So there's that CH3, my other CH3. Here is the hydrogen that got added during my hydroboration. I still have my other alkene carbon attached. And let's just follow the arrows. So I break the bond between 1 and 2 and make a bond between 1 and 6. So 6 was my deuterium. So there I've added my deuterium atom. I break the bond between 6 and 5, and I make a bond between 5 and 4. So I'm going to draw this over here. Here's that oxygen, right? And now I've made a double bond to this carbon atom. I break a bond between 4 and 3, and I put those electrons onto the atom labeled 3. And that methyl group just stays where it is. Here now, I've done nothing to my bond between 3 and 2, so that's going to stay the same. And everything else in this catechol borane has not changed. So there you go. We have now been able to replace this boron with a deuterium, what we call hydroboration protonolysis. Overall, this is just a reduction of a carbon-carbon double bond. So that takes us through the core mechanisms when we're working with boranes, and we're doing electrophilic addition. So far, we've only done electrophilic addition with alkenes. What I'd like to do now is take a step, pause, and then we're going to look at what happens if we do this with alkynes. Alkynes are pi bonds. We can do electrophilic addition across any type of pi bond, whether it's an alkene or alkyne. So I'd like to take time to see how we can use alkynes and what the differences in the products we get are going to be. So to begin our look at how alkynes behave in electrophilic addition reactions, what I'd like to point out is I feel that Sorrell and the Pogel worksheet do a sufficient job of discussing how alkynes behave in the presence of HX and X2. Right? So this is our adding HX across an alkyne and adding X2 across an alkyne. So I'm not going to cover those here. What I am going to cover here, though, is what happens when we try to, first at least, what happens when we try to add water across an alkyne. And so you've seen that we have two different ways we can do this with alkenes. We can do an acid catalyzed, or we can use three ways I should say. We can use acid catalyzed, we can, with H2SO4 and water, we can use mercury acetate and water, we can use hydroboration oxidation. So we have three different ways to do this. Excuse me. When we come to try and do an acid catalyzed addition of water across an alkyne, we find that the combination of sulfuric acid and water is not sufficient. We have to add a Lewis acid into this mixture as well. And that Lewis acid that we're going to use is going to be mercury 2 sulfate, HgSO4. We're going to use that in combination with our strong protic acid, H2SO4, and then finally water, which is what we're trying to get across this double bond. So now, in the first step of this mechanism, the alkyne picks up the mercury cation, and mercury completely leaves that sulfate alone to give our, and this is a Lewis acid base step. And so what we have now is an intermediate that looks like this, where, again, we're going to want to generate that most stable carbocation. This is a vinyl carbocation, but having hyperconjugation does help to stabilize this to a certain extent. Here we've added our mercury to our terminal carbon. Now remember, mercury starts with a 2+ state. It's gaining electrons from the alkene, so it goes to a 1+. It gets a formal positive 1 charge in this case. At this point, water can come along and add in to this vinyl carbocation that we've created excuse me. Here's our carbon atom. And we should keep in mind that we have SO4 2- in each of these steps, balancing these double positive charges that we have. Right? So each step along the way, our formal charges are always balanced. Now at this point, another molecule of water is going to come and deprotonate this oxonium that we've formed. We formed H3O+, and we still have SO4 2-, so all of our charges are still balanced. From here, we are able to protonate this alkene carbon one more time from H3O+. So we'll have a second proton transfer event. So we'll draw that out now more explicitly. There's our hydronium, and we're going to go ahead and protonate at this at the alkene carbon that has the mercury ion. When we do this, we generate again another carbocation, and the reason that we protonate at the mercury is that we're forming a resonance stabilized carbocation at this point. So there's one hydrogen, there's that second hydrogen. We still have our mercury with a formal positive charge, and our SO4 2- balancing everything out for us. This is a resonance stabilized carbocation. Whoops. We already used those electrons, excuse me. So resonance stabilized carbocation. And what we find is that we can draw a second resonance structure where we're delocalizing that positive charge. At this point, right, this mercury can now leave the electrons from the carbon-mercury bond, carbon being more electronegative. Carbon takes those, pushing a pair of electrons onto that oxygen, and we now have now added water across that alkyne. There's the hydrogen we added in this step, and there's the OH we added in this step. So we've added water formally across this double bond, and we have regenerated HgSO4. Sulfuric acid is in there so that we always have a good constant source of proton, but even more so for what we're about to do next. If you see what we have here, we have an alkene with an alcohol directly off of it. And so being the creative types that we are in organic chemistry, we have a very unconventional name for this. We call this an enol. Enols are not stable. The only stable enol that you have encountered so far in Chem 201 is phenol. It is a benzene ring that has an alcohol coming off of it. So we can think that there is a carbon-carbon double bond, an ene, with an alcohol coming off of it. That is the only stable enol that you will see for the entirety of Chem 201. When you get to Chem 202, we introduce new systems that can do special things, but for Chem 201, enols are never going to be around unless they're a phenol. They will undergo a process called tautomerization, which I'm going to show you here next. So I'm going to clear off the board, and we'll see the tautomerization mechanism and why it's so important for us to have that H2SO4 around. So I just really stressed the point of how our enols are short-lived intermediates. They're going to turn into something else. We're never going to have an enol sitting around. So from here on out, as soon as you form an enol in any mechanism, I want you to go ahead and put a set of brackets around it to denote to yourself that this is a short-lived intermediate and you need to do something with it. This won't be the final product of a reaction for you. And so this here now is how we're going to get sulfuric acid to come into play. We still have plenty of water around. That's generally going to be our solvent. We have sulfuric acid. Now, if we consider the acid-base equilibria here, right? Here, sulfuric acid, pKa of -9. Water's my base. Its conjugate acid has a pKa of -2. So we're going to have proton transfer occur between these two species very rapidly to give me H3O plus and the conjugate base of sulfuric acid. From here, recall from our very beginning of when we discussed electrophilic additions that alkenes are weak bases. And so what can happen is that our alkene can accept a proton from hydronium to give us a new resonance stabilized carbocation. And we've done such that we have formed the most stable carbocation we can. Had we added it to the hydrogen to this carbon, the proton added to this carbon, we would have, added to this carbon, we would have formed a primary carbocation, but having this proton add to my CH2 carbon, I form a secondary resonance stabilized carbocation. So let's draw the resonance structure for that. And I'm just going to go ahead and flip that molecule upside down. So now I've got all I did was just pancake flip of the molecule. At this point, when we protonated that alkene, we generated a molecule of water. That molecule of water can come back to serve as a base and deprotonate this protonated carbonyl oxygen, which gives us our true final product, a ketone. So this process that you see here, right, going from an enol to a ketone, is called tautomerization. And outside of phenols, anytime you see an OH directly attached to an alkene, you should immediately think tautomerization. It'll either end up forming a ketone or an aldehyde, depending on substitution of everything in your molecule. And this is the process. So here we see the acid catalyzed tautomerization of an enol to a ketone. So that's one of our ways that we can add water across an alkyne. And we see that if we use our acidic conditions, mercury sulfate, sulfuric acid, and H2O, that ends up forming for us a ketone. Now, going to take a pause here and come right back. We're going to look to see, before I take this pause, in the textbook you have a different set of reagents that you can use to do this as well. You can begin from an alkyne. You can use platinum chloride and water, and this will also add across the alkyne to give you a ketone. I'm not going to go through this mechanism. I'm not going to expect you to be able to produce this mechanism, but you should be aware that this set of reagents, when treating an alkyne, will also produce a ketone. And I advise you to take a look at Sorrel, see what his mechanism looks like. It's not ideal, but it gets the point across, especially because I'm not going to ask you to do arrow pushing for using platinum chloride. Arrow pushing for this, fair game. For mercury sulfate, sulfuric acid, H2O, along with tautomerization, that's all fair game. This, I really just want you to be able to tell me what the products are from the reaction. Okay, so what we're going to do next is we've seen quote-unquote Markovnikov type addition of water across an alkyne. We're going to come back and look at quote-unquote anti-Markovnikov addition of water across an alkyne using a boron-based reagent. So we saw with alkenes that we could get quote-unquote anti-Markovnikov addition of water across a double bond by doing hydroboration oxidation. We can use the same set of reagents to add water in an anti-Markovnikov fashion across an alkyne. So I'm going to start off with my same reagent that I really like to use, catechol borane. And so just like we saw with alkenes, we're going to add in a single step across our, we're going to add in a single step across the alkyne to give our electrophilic boron to the less substituted carbon and our quote-unquote nucleophilic hydrogen to the more substituted carbon. From here, our oxidation mechanism is the same. I'm going to cut out a few steps because we've already seen them once in this video lecture. And I'm going to proceed directly from that hydrogen peroxide anion. Once again, adds into that boron. Here now, we've generated that negatively charged boron. Which undergoes a similar type rearrangement where the carbon group migrates to the oxygen, kicks out hydroxide. we now have our hydroxide anion, which can displace this alkoxide that that alcohol, or that OC group off of our boron. This now takes us to and here, once again, just like with our alkenes, we're going to protonate this from water to regenerate sodium hydroxide. And we see that we have once again formed an enol. As soon as we form that enol, we put it in brackets to tell ourselves that we are going to need to do a tautomerization. However, unlike in our previous reaction where we were using sulfuric acid, here, in this situation, we have a base, right? We just formed sodium hydroxide at the end of, in our last step. And what's really convenient for us is that tautomerization can occur using either an acid, kind of funky looking bracket there, but I wanted to show that oxygen-hydrogen bond more explicitly so that we can see better how a tautomerization occurs under basic conditions. So here's the hydroxide I just formed in my last step. Instead of protonating something, my hydroxide is going to deprotonate that alcohol, which is going to give me a resonance-stabilized anion. We can push a pair of electrons there. That would leave me with 5 bonds on carbon. So I can push a pair of electrons there. Let's give ourselves a little bit more space. And by deprotonating this enol over here, I generated a molecule of water. Here's my sodium. Balance out the negative charges in my resonance structure. Here now I have, going to bring back that molecule of water I got when I deprotonated my enol. Right? We're going to go ahead and protonate from there, which ultimately leaves us with our true product, which we see is an aldehyde. So we can see now that we have 2 methods that we can add water across an alkyne. If we use sulfuric acid, mercury sulfate, and water, we get a ketone. However, if we use, and I'm going to put BH3 in quotations, because you can use any of the BH3 reagents I showed you at the beginning of the video lecture, followed by our oxidation reagents, sodium hydroxide, hydrogen peroxide, you end up now being able to make an aldehyde. Again, from this point forward, this is still considered keto-enol tautomerism. It's just that we don't end with a ketone, we end with an aldehyde. We've seen now how we can do tautomerization with either acids or bases. I can tautomerize the appropriate enol to an aldehyde with either acid or base, and I can tautomerize the appropriate enol into a ketone using acid or base. It just happened to conveniently work out with our examples that base led to the aldehyde this time based on reaction conditions, and acid led to the ketone. Don't let that tell you that. Doesn't mean that you have to use acid to make a ketone or you have to use hydroxide to make a base. either set of reagents will make either ketone or aldehyde. That is strictly determined by the structure of the enol that you begin with. Okay, so that really wraps it up for topic 21 and what I want to talk to you about in terms of electrophilic addition with boron and electrophilic addition of alkynes with alkynes. Alkynes with alkynes, wow, that was a bad one I didn't even plan. Anyways, thank you guys for watching. As always, if you have any questions, please feel free to bring them into conference, lecture, office hours, or make an appointment to see me one-on-one. Have a good one.